Hello, I'm Jim Levis and I'm a Research Assistant Professor at North Carolina State University. Today I'm going to talk about the Solid Waste Optimization Lifecycle Framework and provide an overview of the modeling framework as well as describe some illustrative analyses and results. So to begin, the research background for this is lifecycle assessment is a framework for estimating the environmental emissions impacts associated with a product, process, or system, and solid waste management systems are great for being analyzed by life cycle assessment. That's because solid waste systems consist of all these complex interrelated processes all the way from waste collection to waste separation to waste treatment, biologically or thermally, all the way to final waste disposal. And each one of those processes and mass flows can affect the downstream processes. So basically, to develop a solid waste management system that meets your objectives, that minimizes environmental impacts at reasonable cost, you need to consider all those complex interrelationships, as well as how solid waste generation and composition are changing with time, and how solid waste policy and climate change mitigation policies and other energy policies could also be changing with time. So the research objective of SWOLF is to develop a tool that can evaluate solid waste management performance environmentally and economically while considering all of these factors. So basically we start with waste generation and composition projections that would also include population projections. We could look out 20, 30 years. As well as what solid waste management policies we can consider over that time, whether it's diversion policies or landfill organics bans or incineration bans, etc. We can also include greenhouse gas policies or other energy-related policies, renewable portfolio standards, and include those in an energy system model that can then tell us over time what's the cost of different fuels, what's our electricity mix look like, what's our cost of electricity, and all of these things are then input into the solid waste management process models, and the solid waste management process models are the foundation of all this work. These are life cycle inventory models for all of the processes that make up a solid waste management system, all the way from collection to separation, treatment, and final disposal. And these life cycle emissions models tell us the costs and emissions associated with these solid waste management processes. And these emissions and the emissions estimates can then be used in an impact assessment model to tell us the overall environmental impacts like global warming or smog formation or ozone depletion, etc. And so this LCA model in the blue box, including all those inputs, this is a powerful tool that we can now analyze solid waste management systems from collection all the way through treatment, separation, final disposal, and we can determine what the environmental impacts are as well as the costs. And you could look and do some small what-if analyses and say, well, what if I use this process or instead of this process? What if my travel distance increases to here from what it currently is? And so it's a very powerful model. But the real powerful SWOLF is taking all those inputs and using them in the optimizable integrated solid waste management system model. And the purpose of this is because we have that complicated interrelationships among all the processes, and because everything is changing with time, the optimization framework gives us the ability to systematically look through all the possible technology choices and mass flow potential to determine the optimal system that best meets our objectives as well as meeting all of our policy constraints. And it can tell us the cost, emissions, energy use, and impacts associated with that system. So what are the benefits of optimization modeling for solid waste management lifecycle assessment? Well, firstly, we can ask, how can we minimize net present cost over time? We can do this while meeting diversion requirements or greenhouse gas constraints. We can also do this while considering existing infrastructure and changes to waste composition and generation and the energy system. We can also look at how environmental benefits can be maximized. We can minimize greenhouse gas emissions or fossil energy use or maximize landfill diversion, all while imposing budget constraints. So I want to minimize my fossil energy use, but I can only spend X number of dollars. And we can also look at what are the mitigation costs associated or trade-offs associated with adopting a specific technology or policy. So if we implement waste energy combustion, composting, AD, gasification to biofuels, etc., what do we end up paying per metric ton of CO2e avoided, as well as with landfill, organic bans, diversion targets, or combustion. And the basic idea is here we can start to look at, based on those mitigation costs, we can compare those to other estimates of mitigation costs for things like rooftop solar or afforestation or reforestation, and look at where solid waste management options rank in those mitigation or climate change mitigation policies. So the basis of calculation to the functional unit for SWOLF is the total generated mass of MSW over some decision horizon. We use 30 years here in the illustrative analyses we'll talk about later. So our system boundaries essentially start with MSW being generated and processed through the solid waste management system. And in the solid waste management system, as it's being processed, there are direct gross emissions from, say, landfill gas or waste energy combustion. And there are also emissions associated with the electricity, fuel, and raw materials used in the solid waste management system. So those are additional gross emissions going out the top. And the solid waste management system also generates beneficial products like electricity, compost, recyclables, and then there are avoided emissions associated with that. So our net emissions are the sum of the gross emissions minus the avoided emissions. So the solid waste management system we'll analyze in these two illustrative analyses we'll talk about later is here. We start with 3 different collection options: commingled recyclable collection, mixed waste or residual collection, and organics collection. The commingled recyclables can be treated in a commingled material recovery facility where recyclables can either be recycled and sent to material reprocessing, or they can be combusted for energy. So you could separate out the paper and plastic, let's say, and then combust them. Mixed waste residual collection can also take waste to a mixed waste MRF or a dirty MRF, which then also separates out recyclables or combustibles and has a residual stream that can be combusted or landfilled as well. The mixed waste MRF can also act as a mechanical biological treatment or part of a mechanical biological treatment plan or MBT, and send the organics fraction to be treated in anaerobic digestion or composting. The organics collection also goes to anaerobic digestion or composting, and some soil amendment can be produced depending on the quality of the feedstocks as well as the process, the anaerobic digestion composting processes themselves. So then you have that beneficial soil amendment, and then they also produce residual waste that can be thermally treated or landfilled. The waste to energy facility, so it can take in a variety of combustible or residual wastes, and then from the bottom ash you can recover the metals. The bottom ash itself could also be beneficially reprocessed into aggregate, let's say, and the bottom ash and fly ash can both be disposed in ash landfill or regular landfill. So for the existing system, we included a single stream MRF with 12,000 megagrams per year of capacity, 20 years of remaining life, as well as a composting facility with 6,000 megagrams per year. Megagram is also a metric ton of capacity and also 20 years remaining life. The existing landfill is assumed to have enough capacity to accept all generated waste over the decision horizon. So you don't have to divert anything, the landfill can accept. So we also projected waste generation and composition over that time frame based on the US EPA 2012 MSW facts and figures. We projected population growth over for a city of 100,000 people with an annual population growth of 4% based on Census Bureau estimates over the next 30 years. And then we estimated per capita growth for each material generated to determine how much of each material will be generated in each of the 6 5-year increments. All system changes happen in 5-year increments of population, waste generation, composition, the energy system, as well as policies. And these high-level results show you that the biggest changes over time is paper is decreasing, food waste is increasing, yard waste is slightly increasing, plastic is slightly increasing. So in our illustrative analysis, we looked at 4 base cases. We have a business as usual case where we minimized cost with no new facilities. We still had that composting. So we composted yard waste and we recycled in the single stream MRF. We had a min cost case where we minimized net present cost, and a max diversion case where we tried to maximize cumulative landfill diversion over time, and a min greenhouse gas case where we tried to minimize 30-year cumulative greenhouse gas emissions. We did energy projections were based off of the US EIA Annual Energy Outlook for 2012, the reference scenario. We've done additional work to consider different energy scenarios with different policies, and we'll look at that in the second case study. So the base results show this shows for each of those 4 cases the cost, the greenhouse gas emissions, and the percent diverted. The first interesting thing to see is the min cost was the cheapest, even cheaper than business as usual, but it also reduced greenhouse gas emissions compared to business as usual, and it did this by decreasing diversion, and it actually eliminated some of the yard waste composting in order to reduce greenhouse gas emissions and reduce diversion while saving $3 million. The other thing to notice is the max diversion case costs the most, and it also leads to the most greenhouse gas emissions. And that's partially because you start recycling things that don't actually make sense to recycle, and you start, don't make sense from a cost or a greenhouse gas standpoint. And basically, so it also costs a lot more because you end up doing recycling everything. You build almost every process, and then you burn it, and then you recover all the ash, all the metals from the ash as well as the ash itself. So it ends up being the most expensive. And yeah, then the min greenhouse gas case reduces emissions compared to the max diversion case by eliminating the waste energy combustion and does more selective recycling and landfilling. So these show the min cost scenario results, and it's actually relatively simple. So we have a landfill in every time period as well as a single stream MRF. And basically the landfill grows as waste generation grows, and the single stream MRF actually decreases in throughput as time goes on. And that's because we're actually generating less paper in each time period, as I showed you before, and that decrease in paper leads to the less use of the MRF and to a lower diversion rate. So the interesting thing to note there is with our current processes and our current technologies, even if we don't change anything, it's going to be hard to reach increasing diversion targets just because the composition is changing and there are fewer traditional recyclables in the waste now as there were 10 years ago, and 10 years from now there'll probably be even fewer. So this is the basic scenario. This is the scenario for the min cost case in all the stages. So we have a single stream MRF, and then we have mixed waste collection. We use a landfill. So the max diversion scenario is actually also pretty interesting. More interesting. You see a lot more going on in the figures. Basically, recyclables are separated in a single stream MRF, and then the residual waste from the single stream MRF is also sent to a mixed waste MRF. Mixed waste is also sent to a mixed waste MRF. And so we're trying to essentially get all the recyclables out we possibly can. The residual from the mixed waste MRF then goes to waste to energy to be combusted. And then all the metals are removed from the bottom ash. The bottom ash itself is recovered. So all that ends up actually being landfilled is whatever the fly ash amount is. And the other interesting part is in the first 2 stages, we used the composting facility, and in 2020, we start using the AD for the food and yard waste, as food waste is increasing faster than yard waste is. And then the other important thing to note, the really interesting thing to note here, is also you see in the first stage, waste to energy is a net sink of greenhouse gases, and in every stage after, it's actually a source. And the reason for this is mostly because paper is being replaced by plastic, and another partial, so the biogenic carbon in the paper doesn't count towards your greenhouse gas emissions, but the plastic does, so that's changing pretty rapidly. And the other thing is electricity greenhouse gas intensity is reducing with time. based on the AEO projections, the U.S. greenhouse gas intensity for electricity is going down with time, so that's also having a minor effect. So the max diversion results. So in the first cases, we're composting. We're using the mixed waste MRF, single stream MRF, and waste energy. And then after that, we switch to anaerobic digestion instead of composting. For the min greenhouse gas scenario, this one's actually the most interesting. In order to minimize greenhouse gases, we build a waste energy facility in the first time period. You remember it was a net sink in the first time period. But then after that, we switch to anaerobic digestion for the organic waste. Our food waste is increasing with time. Waste to energy doesn't look as good with time, so we switched to AD in 2015. Now mind you, these results are illustrative, and they're meant for kind of planning purposes and looking to see what makes sense. Obviously, we wouldn't recommend to anyone that you build a waste to energy facility and then you decommission it 5 years later. That would never make sense. This is about minimizing, doing your best, absolute best, and spending what it takes to minimize greenhouse gas emissions. So the min greenhouse gas scenario, in the first case we use waste to energy and we don't manage organics at all, and then after that we use anaerobic digestion and manage our organics, and we don't use the waste to energy. This is an interesting plot showing the trade-offs between greenhouse gas emissions and cost, as well as diversion and cost. So you'll see the green line, it shows how the percent increase, the x-axis, the percent cost increase above the min cost scenario as you reduce greenhouse gas emissions. So if you spend 10% more in greenhouse gas emissions, you essentially reach almost 90% of your potential greenhouse gas reductions. For diversion, something similar. At 10% cost increase, you're now diverting around 45%, let's say, and as you increase that with time, once you're spending 45% more, your diversion only goes up to about 50%. So this tells us this 10% increase in cost is kind of an interesting system where we can really get a lot of bang for our buck. And so this is the results for the 10% increase in cost. And the red zeros show us what the non-zero min cost throughputs used to be. So for the landfill, we used to do more landfilling in the min cost case, and we did slightly more recycling in the single stream MRF, and we didn't use composting. So we start using composting, and we actually start using a mixed waste MRF, and that increases cost, but it dramatically reduces greenhouse gas emissions and increases. Interesting points from this first case study is the first technology implemented that reduces greenhouse gas emissions as well as increases diversion and reduces cost is a single stream MRF. And basically it's win-win-win. In the max diversion and min greenhouse gas cases, AD, composting, recycling, waste to energy, and landfill throughputs all change with stages as waste composition and generation change. So you need to do this kind of stage-wise analysis to really see when and how you should implement different processes. We also found the min cost case did reduce emissions compared to the business as usual case by eliminating yard waste composting, and the changing composition and changes to the energy system can definitely affect your technology choice, especially considering waste to energy. Here are some references with some manuscripts we've written on this if you're interested in learning more. And finally, I'd like to acknowledge the support of the National Science Foundation and the Environmental Research and Education Foundation for their support of this research. Thank you very much.